Hi everyone, it is Mrs. Price, and we are about to start on the second half of chapter 6, which is all about rational functions. So we just finished up polynomials, and now it's time to move into rational functions. So let's jump right in. So the first thing we're going to do is graph the parent function y equals 1 over x. So y equals 1 over x is pretty much like the Mac Daddy of all rational functions. And we'll explain what a rational function is in a minute. But if you take a look at y equals 1 over x, if you graph it on your calculator, you're going to get a graph that looks kind of like this. Now, sometimes calculators can be a little misleading with how the graph looks. You might not see that it actually points up to positive infinity as we approach 0 from the right and down to negative infinity as we approach 0 from the left, but it does. So be careful when you're looking at your calculator. Make sure you understand algebraically what's going on so that you can graph it correctly, and don't let the calculator fool you, because sometimes it has a little bit of trouble when there is what we call a vertical asymptote. And you will see a lot of vertical asymptotes when we get into rational functions. So what is a rational function? A rational function, we're going to call it y equals p over q. It's a quotient of two functions, and both of those functions have to be polynomials. So we just finished studying polynomials, and now we're going to take the polynomials we just learned about, and we're going to divide them by each other. So there's going to be a polynomial on top and a polynomial on the bottom. This one, the parent function, y equals 1 over x, the polynomial on top is y equals 1. That's okay. It's just a constant function, a monomial. And then y equals x is a linear function, still a monomial. So the shape of the graph. So we just said that the graph looks something like this, kind of drawn a little messy there, but this shape actually has a name. The name of this shape is called a hyperbola. So you have these little curves here. These curves are exactly the same, opposite each other. They actually have perfect symmetry for this graph over this line, which is y equals negative x. So you have this perfect, if you were to kind of tilt your head, you have this perfect symmetry, mirror images on either side of that line, and that shape is called a hyperbola. Okay, it says used. Let's fix that typo. Use what you have learned about transformations to predict what the graphs of these functions will look like. So this first one, let's take a look. We are adding 1 to the x value, which means we are going to shift this graph, our parent graph, to the left by 1. And then we're subtracting 2 from the y value, which means we're going to shift our parent function down 2. So when we graph, the parent function has two things that are called asymptotes. I'm going to go back to the parent function for a second. So let's go back to this one. So we have an asymptote this way. That's called a vertical asymptote because it's a vertical line. Now, an asymptote is a line that the graph will get closer and closer and closer to, but never touch. And same thing here, closer and closer and closer, but never touch. Horizontal asymptotes, similar, but horizontal. Now, I'm kind of lying to you because you can actually touch horizontal asymptotes. Technically, with a piecewise, you can touch vertical asymptotes. So asymptotes are not what you'd think of like electric fences. You can touch them, but for all rational functions, for true polynomials over polynomials, you'll never see them touch towards the ends. So in the middle, they might. But towards the ends, a horizontal asymptote is a predictor of end behavior. It's saying what's going on as x gets all the way out there towards infinity and as x gets all the way out there towards negative infinity. And we'll talk more about asymptotes in a minute. But the reason I'm telling you this is so we can do our transformation. We're going to let the asymptotes kind of guide us. So this asymptote, x equals 0 is our vertical and y equals 0 is our horizontal. So what we're going to do for this graph is we're going to shift our vertical asymptote one place to the left. So now instead of at x equals 0, it's going to be at x equals -1. And then our horizontal asymptote, instead of being at y equals 0, it's going to be at y equals -2. So we've taken our vertical asymptote and shifted it to the left 1, and our horizontal asymptote and shifted it down 2. And now we can draw the exact same shape of the function. There were no dilating factors or anything like that, and you end up with a lovely graph. For this guy right here, we have no translations, no horizontal shifts, no vertical shifts. What we do have is a dilation by a factor of 3. So if we take our normal graph passes through 1, 1, and -1, -1. So now we're going to multiply it by 3. So instead of 1, 1, we're going to pass through 1, 3. And instead of 2, 1/2, because it's 1 divided by x, so instead of 2, 1/2, now we're going to pass through 2, 3/2. And so you end up with the exact same shape, just kind of stretched a little bit. So same thing here. So we're going to go to -3, and we're going to go to -3/2, and whoops, and we're going to draw it. So it's the exact same shape as before. Same vertical asymptote, same horizontal asymptote. It's just been stretched a little bit. And we'll see this more as we make tables of values for our graphs. All right, so write the equation for the translation y equals 1 over x if we have a horizontal asymptote at y equals 1 and a vertical asymptote at x equals -3. So let's think about this. If our vertical asymptote is at x equals -3, that means that we have shifted left 3, because normally our vertical asymptote's at x equals 0. It's been shifted 3 places to the left. So what are we going to do? We're going to add 3 to our x value. So instead of 1 over x, we're going to have 1 over x plus 3. All right, our normal horizontal asymptote is at y equals 0. Now it's at y equals 1, which means it's been shifted up 1. So now we have that for our new asymptote, and that means that we have to add 1 to our y values. So remember, translations work exactly how they did for all the other types of functions we've learned. So we've learned quadratics, we've learned roots, we've learned absolute values, similar for polynomials, and now same thing for rationals. Describe the function as a transformation of the parent function f of x equals 1 over x. All right, this one's fun because you are going, in order to simplify this guy, you get to use a little bit of what you learned in the polynomial section. So what we're actually going to do is we're going to divide this, because this really is 2x minus 5 divided by x minus 1. Now, I'm going to do this using synthetic division. So I'm going to set my x minus 1 equal to 0, and I solve and I get x equals 1. I write my coefficients, 2, -5, leave a little space, bring down the 2. 2 times 1 is 2, and I get -3. Now you're thinking, well, that means x1 is not a root. No, it's not a root, but that's okay. What does this tell us? Remember that this number right here, that's the remainder. So if we wanted to rewrite this, 2x minus 5 divided by x minus 1, that would be, remember, we take our exponent and reduce it by 1. So there's no x's anymore. So it would be 2 plus -3, our remainder, over our divisor. So, which is the same thing as 2 minus 3 over x minus 1. So when you're writing these, remember, reduce the power by 1. So our original power was 1. Now it goes to 0. There's no more x's. So we just have the number 2. And then this remainder goes over the divisor. So remainder over divisor. So quotient plus remainder over divisor plus remainder over divisor. All right, so how do we describe this transformation? Well, I would say we've got a couple things going on here. First, we have a translation of 1 to the right. We have a translation of 2 up. And then we have a dilation by a factor of 3. And this negative, which I've kind of run out of space to draw nicely, reflect over the x-axis. So we got a lot going on in this one. Let's see what happens here. So I've rewritten the function here as 2 plus negative 3 over x minus 1. Right here, we've got a graph of our parent function. So this is just what the normal parent function looks like. So let's see here. If we were to shift this to the right one, so I'm going to just do this point right here and just see if you can follow me along. I'm going to go right 1. I'm going to multiply the y value by negative 3. So my 1 is now negative 3. And then I'm going to shift up 2. Whoa. So my new point is at 2, negative 1. So this point right here moved to here. Kind of weird. Now let's take a look at this point. I'll try and do this in a different color. So I'll do this in blue. All right, so this point right here. So I'm going to shift right 1. Okay, and then I'm going to multiply it by negative 3. It's negative 1, so I'm going to go up to positive 3. And then I'm going to go up 2. So I'm going up to 5. So I have a point at 0, 5. What on earth is this thing going to look like? Well, let's see how our vertical and horizontal asymptotes shift, and that'll help guide us. So our vertical asymptote shifted to the right one, so we now have a vertical asymptote at x equals 1. And our horizontal asymptote shifted up 2, so we have a horizontal asymptote at y equals 2. And now we have a point in each of these regions. Without making it absolutely perfect, I'm just going to kind of sketch roughly and follow those asymptotes. And sketch roughly and follow the asymptotes. All right. Okay, so let's learn how to find vertical asymptotes, x-intercepts and y-intercepts. We should also do horizontal, but we're going to focus on those a lot tomorrow. So today we'll do a little bit, but mostly vertical. Vertical asymptotes are any x values in the denominator that cause you to divide by 0 in the denominator only. So when you find vertical asymptotes, you set the denominator equal to 0 and you solve for x. This is your vertical asymptote. So our vertical asymptote is x equals 3. It's those x values that cause you to divide by 0 in the denominator. There's a little more to it, but we won't get into more stuff until tomorrow. We'll just keep it at that today. X-intercepts are the x values where y equals 0. So y equals 0 because they're on the x-axis, which is where your y values are 0. So you set your y equal to 0. Now what happens when we set y equal to 0 is if we were to cross multiply, this whole bottom just gets multiplied by 0. So it really just goes away. And what you end up with is that the x-intercepts are really where the numerator equals 0. So our x is 0. So for this one, our x is 0 and our y is 0. Our y-intercept, you set all your x's equal to 0. You get y equals 0 over negative 6, which is 0. So you end up with, again, 0, 0. One x-intercept, one y-intercept. All right, let's do this again. So to find our vertical asymptotes, you set your denominator equal to 0. So we're going to solve. We get x squared equals 4. X equals plus or minus the square root of 4, which is plus or minus 2. So we have two vertical asymptotes. We have x equals 2 and x equals negative 2. Our x-intercepts, remember, you just have to set the top equal to 0 because the bottom will just get multiplied by 0 and it won't do anything. So you get 2x squared equals 18, x squared equals 9, x equals plus or minus root 9, which is plus or minus 3. So x-intercepts, remember, that's where y equals 0. So we have 3, 0 and negative 3, 0. Y-intercept, you set your x is equal to 0. So you get y equals 0 minus 18 over 0 minus 4. So our y-intercept, if we reduce the fraction, is 9 halves. So we have 0, 9 halves. All right, let's do this one. For our vertical asymptote, we set the bottom equal to 0. I'm having trouble with my stylus here. So I get 2x equals 1, x equals 1 half. This is the equation of a vertical line. So you just call it x equals 1 half, right? And that's your x-intercept, or your vertical asymptote. So I'm going to try to see if I can sketch a vertical line at x equals a half. All right. Let's see. Our end behavior asymptote, which is the same thing as a horizontal asymptote. So without telling you too much, I'm just going to tell you for now that, and I'll teach you about this tomorrow, our horizontal asymptote is at y equals 5. And there's a reason for this, and it has to do with the fact that when you have the same degree, top and bottom, you just divide your leading coefficients. So 10 divided by 2 is 5. So we have a horizontal asymptote at 5. So 1, 2, 3, 5. And there's our horizontal asymptote. All right, so our domain is all reals except at the vertical asymptote. So you could write x not equal to a half. I'm going to write it in interval notation. So negative infinity to a half, union 1 half to infinity. Our range is all y values except the horizontal asymptote. So negative infinity to 5 and 5 to infinity, not including the 5. All right, let's find our intercepts. So our x-intercept, we set the, so x-intercept, set the top equal to 0, 10x equals 4, x equals 2/5, 4/10 or 2/5. So we are intersecting the x-axis right, like, so this is at a half. So it's really hard. It's in between, it's right here. It's just hard to draw in between 0 and a half. So there's our x-intercept. So 2/5, 0. Okay, and then our y-intercept, remember you set y-intercept. We set our x is equal to 0, so we get y equals negative 4 over negative 1, or 4. So we're going to intercept the y-axis at 4. This is going to be a super steep graph. So and there's a table here. If you want to make a table, I'm not, to me, if you have the asymptotes correct, I'm happy. That doesn't bother me if you're not perfect with all of your values. This is so steep. It's really hard to draw. It should have a curve here, but it's just so steep. It's just hard to draw. And then there, of course, should be another graph up here. But again, it's going to be really hard to draw. If you wanted to make a table, just plug in a few x values near your asymptote. So for example, if I plug in x equals 1, I would get 10 minus 4, which is 6, over 2 minus 1, which is 1. So I have the point 1, 6, which I didn't do bad with drawing right there. And then if I plug in 2, I get 20 minus 4, which is 16, over 4 minus 1, which is 3. So I have 16 thirds. And then they start to get kind of ugly. At negative 1, Negative 10 minus 4 is negative 14 over negative 3, so you have 14 thirds. Not very pretty. I'm happy if you just get your asymptotes right and sketch your intercepts and sketch your graph. All right, let's try another one. So for this one, vertical asymptote. So vertical asymptote, set your denominator equal to 0, because remember, you can't divide by 0. So anything that divides by 0 is bad. So that's why those end up creating those asymptotes. So we end up with x equals plus or minus 2. So we have a vertical asymptote at x equals 2 and x equals negative 2, which have already been drawn, which is kind of nice. Our domain, if you have to exclude two values, honestly, you can either write the domain, I'm going to put it up here. So you can write it as x not equal to 2, x not equal to negative 2. I'm going to write it in interval notation just because that's what I am so used to doing. Negative 2 to 2, 2 to infinity. And that would be all reals except for negative 2 and 2. Our end behavior asymptote, we have the same degree top and bottom, so we end up with an end behavior asymptote of y equals 2. So our range would be all reals except 2, possibly. Let's take a look at the graph and just make sure. First, let's find our x-intercepts. So our x-intercepts, if we set 2x squared plus x minus 21 equal to 0, looks like we're going to have to factor this guy. So we have a 2x, we have an x. So only factors of 21 besides 1 and 21 are going to be 7 and 3. So we're going to go 7 and 3. And that way, if we do a plus 7 and a minus 3, our inner and outer becomes 7x minus 6x, which works. So our x-intercepts, if we set each of these equal to 0, we get negative 7 halves or positive 3. So our x-intercepts are negative 7 halves, 0, and 3, 0. So if I sketch those, so I've got 3, 0. So negative 7 halves is negative 3 and a half. There's my two x-intercepts. My y-intercept is, let's see, set those x's equal to 0. So I get y equals negative 21 over negative 4, or 21 fourths, which is a little over 5. 1, 2, 3, 4, 5, somewhere right up here. All right, so we have 0, 21 fourths. Now, these graphs, again, you can follow your asymptotes and just let them guide you, but the middle part you might have to do a little work. So I'm going to go ahead and just sketch these graphs right here. So we got this guy, and we got this guy. All right, so those follow the asymptotes just fine. Sometimes what's going on in the middle can be a little unusual, so I'm going to go ahead and just plot some points at x equals negative 1 and 1. So at x equals negative 1, f of negative 1, we get 2 minus 1 minus 21 over 1 minus 4. So negative 20 over negative 3, or 20 thirds. All right, so 6 and 2 thirds, so we're at 1, 2, 3, 4, 5, 6, a little higher. All right, that's hard to see. There we go. And then f of 1, 2 plus 1 minus 21 over 1 minus 4. So 3 minus 21, so negative 18 over negative 3, so 6. So I'm at here. And so what ends up happening if I follow my asymptotes, so I'm going to end up with some kind of like a parabola looking thing in the middle here. Sometimes it can go up and down. In this case, it just goes up on both sides. So I end up with something like that. It's kind of a weird graph. Oh, I'll put these in here, 20 thirds and 6. All right, and I end up with that. Now, what does that mean for me? The range can be a little awkward because we don't know for sure that the y-intercept is actually the minimum of this parabola. Is it really the minimum of the parabola? Let's see. Yeah, just not sure. So I'm not going to have you worry too much about the range. I can tell you for sure it's negative infinity to 2, but then there's no graph from 2 to around 1, 2, 3, 4, 5 to 21 fourths. So if we put 21 fourths to infinity, we'd probably be really close. I don't know if we'd be perfect, but that's okay. That's getting a little too picky.